We will now use the concepts we developed in rotational motion to solve problems. Well, to do that, you need to be familiar with some of the equations we developed earlier. Is that right? Now, it is easier to write down the formulae for linear motion and then rewrite the corresponding equations for rotational motion. That is much easier. So let's do that to begin with. For linear motion, v equal to v0 plus at is our first equation of motion. How does that translate to rotational motion? Omega equal to omega 0 plus alpha t. X equal to x0 plus v0t plus 1/2 at squared becomes theta equal to theta 0 plus omega 0t plus 1/2 alpha t squared. V squared equal to v0 squared plus 2ax becomes omega squared equal to omega 0 squared plus 2 alpha theta. F equal to ma. What will be the equivalent equation for rotation? Tau equal to I alpha. Work done in linear motion is force multiplied by the distance. Work done in rotational motion is the net torque multiplied by the angular displacement. Kinetic energy in linear motion is 1/2 mv squared. Kinetic energy of rotation is 1/2 I omega squared. Linear momentum P equal to mv, angular momentum L equal to I omega. Kinetic energy of rolling is 1/2 I omega squared, that is kinetic energy of rotation, plus the kinetic energy of the motion of the center of mass, that is 1/2 mv center of mass. Mostly we will be using these equations. Alright, let's look at the problem. A 3.5 kilogram cylinder of radius 15 centimeter is initially at rest. A rope of negligible mass is wrapped around it and pulled with a force of 17 Newton. Find A, the torque exerted by the rope, B, the angular acceleration of the cylinder, and C, the angular velocity after 5 seconds. In this problem, we have a cylinder and a rope is wrapped around the rim of it, and if I pull on the rope, see what happens? The cylinder rotates. When you pull on the rope, the cylinder rotates. Now tell me, what is the torque? The axis of rotation is through the center. This is the axis of rotation. Therefore, the torque arm is the perpendicular distance between the axis and the force, that is the string. That means the torque arm is the radius of the disc. Is that right? Because this is the force where I'm pulling, and the force, the distance of this force from the axis is the radius. Therefore, the torque will be the force multiplied by the radius. Well, that concept must be clear. Okay, let's go back and do the problem now. Well, this is our cylinder and the rope is wrapped around it, and we pull the rope by a certain force. The radius of the cylinder is 0.15 meter. The force that you apply on the rope is 17 Newton. So, mass of the cylinder is 3.5 kilogram. Its radius is 0.15 meter. and the force applied on the string is 17 Newton. F equal to 17 newtons is at right angles to, as I showed you, this is the radius, and that F equal to 17 Newton is at right angles to this radius. Therefore, the torque produced by that force is R times F sine theta. Remember, sine theta is 90 degrees, therefore sine theta is 1. Theta is 90 degrees, therefore sine theta is 1. So torque equal to R times F, that is 0.15 times 17 is 2.55 meter Newton. What do you want to find in the B part? We want to find the angular acceleration. Now, what is the equation that connects the angular acceleration to the torque? You see, in linear motion, F equal to ma. In rotational motion, tau equal to I alpha. So, if you can now find the moment of inertia of the disk, we know tau, therefore we can find the angular acceleration. Alright, let's now find the moment of inertia of the disk. A cylinder is the same as the disk of radius r. What is the equation for the moment of inertia of a disk? I equal to 1/2 mr squared. Is that right? Now that will be 0.5, that is 1/2. Mass of the disk is 3.5 kilogram and the radius is 0.15. So 1/2 mr squared is 0.04 kilogram meter squared. And now tau equal to I alpha, therefore alpha equal to tau divided by I, and we have those values. Tau is 2.55 meter Newton and I is 0.04 kilogram meter squared. Therefore, the angular acceleration is 63.75 radian per second squared. You can see how simple these become once you approach them systematically like this. What is the next question we need to answer? Find the angular velocity of the cylinder after 5 seconds. Well, you know the angular acceleration and you know the initial angular velocity. What is the initial angular velocity? The disk is initially at rest. So the initial angular velocity is 0. The angular acceleration we know and the time we know. Therefore, we can now say omega equal to omega 0 plus alpha t. Is that right? Alright. Omega 0 is 0, t equal to 5 seconds. Omega f equal to omega 0 plus alpha t. And that will be 0 plus alpha we calculated, 63.75 radian per second squared, times 5. That is 318.75 radian per second. And that is the angular velocity of the disk after 5 seconds. Alright, let's try another problem. A wheel mounted on an axle that is